kind of move on. So hopefully we feel pretty comfortable with the bonding force curve. Your textbook also indicates that if we want to consider now bonding energy, that the same curve can be used to generate that data. Or in other words, thinking of the opposite, it is known that the force information is generated by taking the derivative of the data in an energy versus inter-ion distance A. So if we know the same information for energy, if we take the derivative of that data, we can get the force data. So that's what that's indicating down here. If we have the energy data in our second graph and we are able to take the derivative, we can generate the force curve. And because the integral is the opposite of that, if we take the integral of the force curve, we generate the binding energy curve. We saw before that when the force of attraction was balanced with the force of repulsion, we crossed the x-axis. So that was the ideal bond length. And so at this point, this is where the slope is steepest. And notice that it is steepest here, and that is indicated as being the most negative value on the curve. So we're actually taking the opposite of the slope values, negative of the slope values. Okay. Perhaps I'll re-say that again here. If we're taking, here's negative slope values on this curve, and that explains the negative data here. And once we find the binding energy minimum, we'd expect a slope value of 0, and that's reflected as our x-intercept in our bonding force curve. And then eventually these data go to positive slopes, and we see the positive data set generated in the bonding force curve. That's more clear. Apologies for that. Okay. So a takeaway from this idea is that if we're able to generate the bonding energy curve now, we know the bond strength or the bond energy value of the two ions. So we know the energy associated with keeping these two together. And so that's generated by the depth of the well here. The deeper we go, the stronger the bonding energy between the two. If we wanted to break the bond, we would know how much energy to apply to break the bond and send ions as far away from one another as possible. So that represents the y distance on this binding energy graph, moving from the bottommost well to the x-axis. Okay, so that is to say the trough indicates the strength of the chemical bond in this ionic bond. Okay, so what we've seen so far is we've used our planetary model and been able to generate a hard sphere model for packing ions in ionic bonds. We saw that the ionic radii could estimate the bond length as a sum. And we mentioned briefly earlier that that it's known that there's some volume adjustment due to the electron transfer. And so some other more advanced models apply a soft sphere model to what we've done here. Okay, so to better visualize that contraction, here you see in taking that outermost electron and transferring it to the chlorine neutral atom to make chloride, that the remaining planetary model here with just the 2 level, the principal quantum number 2 orbitals filled, is contracted as we go to the anion. So this was the idea emphasized earlier, that the cation has contracted. Better depiction there. And then once we add the electron to the outermost orbital, shown here, that the anion has to expand in its size. So the anion has added volume. Okay. Okay. So the sort of text box here emphasizes that electrons ended up drawn closer to the nucleus because the relative charge difference now between the same number of protons and the fewer number of electrons leads to the contraction there. And because we have force of repulsion between electrons and putting the extra electron into another orbital that was once occupied, that 3p5 becoming 3p6, there has to be some additional volume to accommodate that. So electrons are less attracted to the nucleus because of that added electron. Okay, so what else can we do with this radius and hard sphere model approach to understanding ionic bonds in ionic materials? Well, we can think about a coordination number, Cn, and we'll show that a simple ratiometric understanding can predict what coordination number is most likely for certain ionic compounds. So here's a situation where the cation, the smaller cation, has a small radius, r of 0.2, and the anion, being larger, has a larger radius of capital R of 1. So clearly having a coordination number of 1 is possible. We would have opposites attracting, and that would happen. Now we also have the other side of the cation that's available for ionic bonding, so we could position another anion on the other side of that cation. So in this case, positioning two anions on opposite side of the same cation is possible. And that would lead to a coordination number of 2. So that is the number of oppositely charged ions at this cation is 2. There are 2 coordinated anions. How about extending this further? Well, given the size obligations of having a radius of equivalent value 1 against the cation of radius value 0.2, if we consider a coordination number of 3, so that is 3 anions surrounding the same common cation, that we start to see some gaps in the hard sphere packed model for bringing all these ions together. Doing this leads to less efficient packing in the hard sphere model, and this allows us to think about the maximum ratio values that could exist between these radii. This is more emphasized when we consider increasing the coordination number even further. So 3 might be possible for this arbitrary 0.2 to 1 ratio value for the 2 ions in question. Going to 4 emphasizes this different. So if we have to maintain hard sphere contacts here, it's impossible to bring 4 anions into contact with that common cation because we end up breaking the hard sphere model here where there's overlap. So here we can predict this would be unstable if we consider the ratio of the radii. So we'll see here this is tabulated for us, and that the ratio here of 0.2 to 1, giving an outcome of 0.2 as the ratio between the two, indicates that coordination number of 3 is allowed. Okay. So calculating the ideal ratio where there's perfect contact point between the inner cation hard sphere and the larger anion hard spheres, using a geometric analysis that I won't go into, you can see here that we can calculate what that ratio would be. So the ideal ratio using trigonometry with an angle of 30 degrees here, gives us a ratio of 0.155. So this tells us sort of a minimum limit to the coordination number value. So if we're going to consider coordination number values of 3 with 3 anions for the cation, we would want the ratio to be a minimum of 0.155. And we'll be able to accommodate slightly larger inner cation radius, so slightly larger cations to a certain threshold, in which case we'll be outside of the coordination number 3 and consider a larger coordination number 4. So as we go to larger cations, putting the same number of anions around this, we might expect that coordination number of 4 will be allowed at some point. And so the R over R is going to be much greater than this 0.155. So other geometric analyses have been done on these other coordination number options, and those values are going to be listed in the next table here. Okay, so we spent some time thinking about coordination number 3. We saw how a geometric analysis could give us a minimum ratio value of 0.155 to consider. So here's the equation. So here's the radius, again, of the cation, the central feature, so that's shown in black. And then the radius, capital R, of the anions being considered to be positioned around the ion here is there. Okay. And so what have we observed here? It's known that for most coordination number 3 ionic compounds, that the radius ratio of cation to anion lies between 0.155 and 0.255. Kind of an empirical result there. Geometric analyses has shown also that if we're to consider the coordination number now of 4, that the radius ratio should be 0.255 at minimum and as large as 0.414. And this tetrahedral arrangement is not like I listed on the previous slide, but rather takes advantage of three-dimensional space to give us that tetrahedral packing that we saw. If we're forced to accommodate even larger cations, then we're going to have to increase the ratio past that limit, and we're going to go now to a coordination number of 6, and that's going to give us the octahedral packing arrangement in certain ionic compounds. And we'll see that until a ratio of 0.732 can be had, in which case we need to position even more anions to accommodate a coordination number of 8. And this will give us a cubic type situation here rather than the octahedral that we saw above here. And then when this ratio value gets very close, that is when the anion and cation are roughly the same size, we're going to see very large coordination numbers, something like 12. So here's similar information here. Those limits to the coordination number values are listed at left. And some example compounds that are known are listed down the way here. Most materials in coordination number 4 will try to take advantage of a tetrahedral arrangement, but some square arrangements are known where other sort of bonding circumstances contribute to the shift from tetrahedral to square packing. Okay, so hopefully you can see here that by simply knowing ionic radius information, that we can predict something about the structure and ultimately how atoms are packed past the single bond level to 3 dimensions. And this will speak to the overall properties of the material and the strength and ultimately potential melt point and boil point and other information about the material. Okay, so how can we use this as an example? Here's another sort of set of questions here. So we might be asked to estimate the coordination number for a cation in a certain ionic compound. Okay, so the coordination number of the cation. So we need to know what is the metal in question. And if we know the radius information of each ion in the ionic compound, we can address this. So there's a bunch listed here from your textbook. We won't handle them all, but you could. We'll just handle a couple here together first. And then we'll turn back to that table of information and try to predict what the coordination number should be. Okay, so perhaps considering calcium oxide, if we knew the calcium ratio, calcium is the smaller cation in this ionic compound, and the oxygen is the anion, so it is the larger species. So the cation value, radius value for calcium is listed above, and so here we have this 0.160 nanometer value, so that can be our numerator. And then in the oxide, we have that radius information as 0.132 nanometers, that can be our denominator. Notice that units cancel, so nanometers over nanometers, so we end up with a unitless value here. So we do not need to go into meters for this exercise. And we have a radius ratio of 0.8 values here. Something to note here is we've always been putting the smaller value in the numerator. So if you had accidentally considered doing 0.132 divided by 0.106, you would end up with a ratio value that is greater than 1, and these values weren't on our table. So we're not going to, that's one way to identify if you've made a mistake. The smaller value goes in the numerator, okay? Okay, so for calcium oxide, we've got a coordination, we can determine the coordination number now that we have the ratio of radii, 0.8. So if we go back to our table, the 0.8 value lies in this range, 0.732 to 1. So we would predict that we should see a coordination number value of 8 for this compound. And so that calcium oxide should be similar in coordination number to these other ionic compounds. Okay, for magnesium oxide, you can see the stoichiometry, the number of calciums, number of oxygens is similar. So you might otherwise, by formula, predict that they might have similar coordination number, but let's inspect by radius estimate. And so now with radius information for magnesium, the smaller the cation here, that's our numerator, 0.078. We see that here. The denominator value better be larger than that if we're doing things correctly. And so for oxygen, again, 0.132 is the value down there. So we saw that earlier. We used that earlier here. And so this time the ratio is much smaller, 0.59, unitless again, nanometers cancel nanometers. And so we can turn back and look at that. So 0.59, this time that lies in this territory here. And so the magnesium oxide, while similar in formula to calcium oxide, would actually be predicted and is known to have a different coordination value at that cation. So there are going to be 6 oxygens that surround that magnesium versus the 8 oxygens that surround that former calcium in these two examples. Okay, and so that's how we kind of use this information to help predict structure. Okay, we'll end the video there, and we'll cover other bonding in the last and final video of this chapter. Thank you.